Finite Math, Basic Carbon Dating. In this video, we're going to find the remaining amount of carbon after a certain number of years, and find the age of a carbon material. As you go through this video, on the top left, you're going to notice some icons. We'll talk about the process, some practice, and then what you need to do to get really good at it. Remember, it's not magic, it's math, so let's get started. Uninhibited radioactive decay. All radioactive substances have a half-life, which is the time required for half of the radioactive substance to decay. The amount A of radioactive material presented at time t is given by A at t equals A sub O e to the kt. A sub O or A naught is the original amount of radioactive material. K is a positive number that represents the rate of growth, or K can be a negative number that represents the rate of decay. And T is the time in years. In carbon dating, we use the fact that all living organisms contain two kinds of carbon, carbon-12, a stable carbon, and carbon-14, a radioactive carbon with a half-life of 5,600 years. Let's do an example. An artifact originally has 16 grams of carbon-14 present. The decay model A equals 16e to the negative 0.000121 t describes the amount of carbon-14 present after t years. Use the model to determine how many grams of carbon-14 will be present in 6,720 years. A at t is the amount of radioactive material at a certain time. Since we're talking about 6,720 years, t is going to be 6,720 years. You're going to notice that I also put it on the right side in for t. We need to use our calculator. We're going to take 16 times e to the negative 0.000121 times 6,720. Now every calculator is different, so you need to look at your calculator and first find the e, and then make sure you put the exponent in correctly. When you do that, you should get 7.09555632. In 6,720 years, approximately 7 grams of carbon-14 will be present. You get to try this one by yourself. Pause the video, complete the question, and then press play for us to work it together. Okay. An artifact originally had 16 grams of carbon-14. The decay model A equals 16e to the negative 0.00121 t describes the amount of carbon-14 present after t years. Use the model to determine how many grams of carbon-14 will be present in 8,118 years. T is going to be 8,118 years, so that's what I'm going to put in for t. We need to use our calculator. We'll take 16 times e to the, now this is to an exponent, negative 0.000121 times 8,118. This should give you 5.99131812. Now if we look at the question, it asks us to round to the nearest whole number. So this is approximately 6. In 8,118 years, approximately 6 grams of carbon-14 will be present. Let's look at this one together. The function A equals A naught e to the negative 0.00770x models the amount in pounds of a particular radioactive material stored in a concrete vault, where x is the number of years since the material was put into the vault. If 800 pounds of the material are placed into the vault, how much time will need to pass for 272 pounds to remain? Round to the nearest whole number. Let's look at our equation. Well, A of x is the amount of radioactive material at a certain time, and the time is what we're looking for. A sub naught is the original amount of radioactive material. Let's fill in what we know. If 800 pounds of the material were placed in the vault, so that's our original amount, how much time will need to pass for only 272 pounds to remain? Now let's solve. First thing we're going to do is we're going to divide by 800 on both sides. This gives us 0.34 equals e to the negative 0.00770x. To get rid of the e, or to cancel the e, we're going to take the natural log of both sides. The natural log of 0.34 is negative 1.078809661 equals. Now on the right side, natural log and e cancel each other. That leaves us with the exponent, negative 0.00770x. To get x by itself, we're going to divide by negative 0.00770. This gives us 140.105 and a whole bunch of numbers. But we need to round to the nearest whole number, so that's approximately 140 years. How much time will need to pass for only 272 pounds to remain? 140 years. You get to try this one by yourself. Pause the video, do it, and then press play so we can work it together. Let's see how you did. The function a equals a naught e to the negative 0.00693x models the amount in pounds of a particular radioactive material stored in a concrete vault, where x is the number of years since the material was put into the vault. If 400 pounds of the material are placed in the vault, how much time will need to pass for only 187 pounds to remain? Round to the nearest whole number. We're going to use the same method. Well, we know that we're going to start with 400 pounds, so that's going to be a naught. And what we want in the end is 187 pounds. So let's put 187 in for what we want, and 400 is what we started with. Now I need to get e to the negative 0.00693x by itself, so I'm going to divide by 400. 187 divided by 400 is 0.4675. You do not want to round any of these numbers until we get to the end. What I need to do now is take the natural log of both sides. The natural log of 0.4675 is negative 0.76035593. The natural log and e cancel, leaving us with the exponent, negative 0.00693x. We're going to divide by that, and it gives us 109.719 equals x. We need to round to the nearest whole number, so it's approximately 110 years. How much time will pass for only 187 pounds to remain? 110 years. Find the half-life of a radioactive element which decays according to the function a of t equals a naught e to the negative 0.037 t, where t is time in years. What we want to do for this one is we're going to find the half-life. What we want in the end, remember this is the amount at time t. Well, we want half of the original amount. So 1/2 of the original amount is 1/2 times a naught. Do you notice that we have a naught on both sides? Let's divide by that. That gives us 1/2 equals e to the negative 0.0371 t. We have e, so we need to take the natural log of both sides to solve. The natural log of 1/2 is negative 0.693147118, and that equals negative 0.0371 t, because natural log and e cancel. Next we divide, and we end up with t is 18.683. Round to the nearest tenths, and we end up with 18.7 years. You get to do this one by yourself. You're going to pause the video, do it, and then press play for us to work it together. Find the half-life of a radioactive element which decays according to the function a of t equals a naught e to the negative 0.0386 t, where t is time in years. Well, here's our formula. We want to find half of it. So remember, a naught is our original amount that we have. So we want to end up with half of the original amount. We're going to divide, and we end up with 1/2 equals e to the negative 0.0386 t. We need to take the natural log of both sides, because the natural log and e cancel each other. The natural log of 1/2 is negative 0.693147118, and that equals negative 0.0386 t, our exponent. When we divide, we end up with 18.0038 equals t. It asks us to round to the nearest tenth, so that's approximately 18 years. Let's read this one, and then you're going to work it by yourself. Suppose an Egyptian mummy is discovered in which the amount of carbon-14 present is only about 3/5 the amount found in living human beings. The amount of carbon-14 present in animal bones after T years is given by y equals y naught e to the negative 0.0001216t, where y naught is the amount of carbon-14 present in living human beings. How long ago did the Egyptian die? We're still using this formula. Y is the same thing as the amount at a certain time, and y naught is the same thing as a naught, the original amount. Okay, pause the video, do it, then press play, and we'll work it together. For this one, the amount of carbon-14 present is only 3/5 the amount found in living human beings. So for this one, we're going to take 3/5 times the original amount, and that's the amount in a human being. And we don't even need to know that to solve. We're going to divide by a naught. That gives us 3/5 equals e to the negative 0.0001216t. We're going to take the natural log of both sides because the natural log and e cancel each other. The natural log of 3/5 is negative 0.510825624 equals negative 0.0001216t. Dividing by that number, we end up with 4200.868616. Round to the nearest integer as needed, and this gives us approximately 4,201. About 4,201 years ago, the Egyptian had died. What do you need to do now? You need to practice. Did you like the video? Why not like it? Did you really like it? Come on and subscribe. Did it help you? Why don't you share it with a friend? Remember, it's not magic, it's math.